Okay, let's keep talking about the methods and properties of NumPy's arrays. We talked about the indexing of arrays. Now we are talking about the other things. So let's first define this is from 0 to 9, and we use a tuple 2, 5 to reshape this array to a 2 by 5 array, and A will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we wanna show the different properties of this array, and this is n-dimensional. So the number of dimensions. Okay, so there are 2 dimensions because it's 1 dimension, the second dimension, and this is what we talked about before. And this is the shape. Is how many dimensions do you have, and how many columns and how many rows do you have? A dot size is 10. So how many elements and items do you have? And the funny thing is that, very interesting, you can also have the transpose of the array. See, this is something that you can never do with a list. So array is a very magic data type. A dot D type, and you can see that this is so the item of this is an integer, 32-digit integer. Okay, let me see if I can make it. Maybe I can just show it like this. Okay. Yeah, maybe this is better. Maybe this is better. Yep. Arithmetic operators, element-wise application. So you define a array from 0 to 3, and B is this array, and A times B will be, let me just use it, copy, paste, and A times B will be the element-wise multiplication. So 0 times 2 equals 0. 1 times 3 equals 3. 2 times 2 equals 4, and 3 times 4 equals 12. B minus A will give you the element-wise subtraction. Okay. 2 minus 0 equals 2, 3 minus 1 equals 2, and 4 minus 3 equals 1. And similarly, if you have a C like this, and but C is a list. Remember that C is a list. A list times an array, A times C. She says this is A, and this is C. Okay. A times array, what do you get? To make it easier to see that, so 0 times 2, you got a 0. 1 times 3, you got a 3, and 3 times 5, you got a 15. So if one variable is an array and the other is a list, then the multiplication between an array and a list will be element-wise. It will be very similar to the multiplication between an array and another array. Okay. Also, we can also use the plus equal and multiply equal, which is so 1 plus equal B is basically a very concise way of writing A equals A plus B. It's actually you assign the value of A plus B to A. Okay, and similar to the multiplication. So C, A now is A, and this is B, and A. Let me just define C and equals A. C, they're the same. Okay, B, and A equals A plus B, we get A as A element-wise plus. Okay, you got a 2, 4, 4, 7. You can also have C plus equal B. Then you have C equals B plus C, and C will be the same as A. And it's very similar to for the multiply equal. For example, A is this. Now C is also this, and B is this. Let's do A equals A times B, and C equals no, C multiply equal B. And what do you get? You get A as 2 times 2 equals 4. And you have, let's just look at the beginning, the first and the last item. 7 times 4, you get 28. And you have C the same. Okay. Introducing Numpy arrays. You can also use type A to take a look at the type of this, and it's going to show you that this is Numpy's array. Okay, you can also use the D type. Then you are taking a look at the type of the elements, not just the type of this array. Okay, because the type of the array is an array itself. You can also do a dot item size. Okay, so 4 bytes per element. If I just change it to say A equals A times 100, then I will have A like this. I guess it may not change. What about this? And okay, now you find that the each element has becoming, the bytes have become greater. It's a larger number. Okay, let me so you can also return a shape, or you use a shape A. It's the same. We have tried this for a number of times. Okay, shape is, maybe I should use this. Okay, yeah. We should use np dot shape. Maybe I should np dot shape. Here maybe I should use np dot size. A dot size and np dot size. Okay, or size A. Okay, size is not defined. So I have np dot size. Let's say integer. How about I just convert it into an integer? No, I cannot do this. I have no idea. Like size is. Sorry, please just ignore it. I think Python 3 have changed it. Okay, I should just update this. Okay. Yeah, but this is not really important. You can just use a dot size, and you can also check the number of bytes that the array uses in memory. Bytes 2, and like I said, the number of dimensions we have talked about this one. A is, if I use a dot reshape, okay, 2, it's gonna be a dot endine. It's gonna be well, number of end dot shape. I should assign it to A. Okay, now so I have 2 dimensions, and and it's 2 by 2. You can also create a copy of this array by doing b equals a dot copy, and you will have b, a as this, and b also as this. What about if I convert b and a will become smaller? What about b? B is the same. It's just a copy. Okay, it's not a pointer. B is not pointing at A. B is just a copy of A. Okay, and you can also convert a array to a Python list, which is pretty easy. You can basically just use a.toList, and also you can use this, but this gives you something different. It's okay, be very careful. List A will give you a list of arrays, but toList will convert this array to a list of lists, okay, or a list. To make it a different. So this is very accurate. For one-dimensional arrays, lists also work equivalently, but it's slower. But for multi-dimension arrays, a list and toList can work differently. Okay, what about b equals a range? Okay, a.toList and list. Okay, they are the same. But if I make it to reshape, then I have this. And what about this? So you can see that the list of A works differently from a.toList for multi-dimensional, more than one dimension arrays. Setting array elements. You can also set the array elements, like this is A, and if I want to have, this is what we learned, if I want to have the first element, I have this 0, and then what if I want to have the last one? I can have this. Wait, oh, I'm sorry. I should have the first row lost the column. No, the second row lost the column, and it's 9. What about I want to change the first one to this, and the last one to this, and A will become this, and you can see that the first and the last column, the first and last, they are replaced by the new numbers. You can also set all values in an array to 0. For example, use A field 0, you will have a. Remember, this change is in place. That means when you do this, A itself will be changed. So if B is A dot, wait, let me just okay, then this is A, and let's take B as A's copy, and this is B, and what about change A to all zeros, and B stays the same. Remember that B is not pointing at A, B itself is a copy of A. Okay. And I can also change all of the values to 5. Then B, A is this. Well, B is still this. What about I create a, the same A, and C is A, C, and A, I change it to 5, and A is this. What about C? You see, an array is mutable. Okay, an array is mutable. So if I change all the elements of A to 5 or to some other, if I want to change the value of A, then C will be also changed. But B is not changed because B is just a copy of A. Similarly, okay, if I change this to 888, then A will become this, and C, we find that the last one is also changed. Well, B is never changed. Okay. You can also make all the elements, so all the items of A as, well, I probably should use this as 0. Then A will be all 0. So what if I do this? A is still changed. If you just use one column, then without a comma, then all of the values will be recognized and you want to change all the values. If you just want to say I just want to change the second column to 2, then A will become like this. And if I want to change the second row to 3, okay. Beware the type collation, and if you assign a float into an integer array, will truncate decimal parts. Okay, so it's very important. If I have type of A must be an array. Okay, and so it's integer 32. That means all of the elements in this array is integer. And I wanna, and this is A, and I wanna change it to all of them to 9.99. And A will just have, A's second row will only be changed to 9, not 9.99. Remember that this is not rounding. Okay, by rounding it should be rounded to 10, but here we just have 9. Okay, fill has the same behavior. Like if I do fill minus 4.8, it's gonna make A as minus 4. Okay. Multi-dimensional arrays. And this is actually we were using the multi-dimensional arrays, so we can basically skip this. And there was just one thing. If you don't specify, well, maybe I should okay. If I don't specify the number, the number as row or column, it actually automatically recognizes as a row. Okay, you have to specify that this is a column, then it's going to be recognized by Python as the second column. Array boosting. It can allow you to add a constant to a matrix or multiply a matrix by a constant. For example, you have, actually I showed this a little bit. So if A times 2, okay, each of the elements will be multiplied by 2. Broadcasting, okay. So this is kind of broadcasting. So basically, when a plus, like this is a plus 5, you will have 5, 6, 7. Let's do 8 plus 100. Okay, it's kind of like you plus the see. Let me create another array. Np dot arrange 100 to 110 dot reshape. And B is no, sorry, I should have sorry, I should have times 100. Np dot once. Oh, I should have this. Yes, and this will be right. And B is 100, and A plus A is this. And A plus 100 will give you 100 to 109, and A plus B will also give you this. But because B is float, B's element is a float data type. So that's why we converted to a float. But you get what I mean. So basically, when you use A as an array to plus 10, you are broadcasting 10 to a 1 by 5 array with all the elements as 10 in this list. Here in my example, when you do A plus 100, you're actually creating a 2 by 5 matrix, 2 by 5 two-dimensional array with every element as 100 in my example here. Similarly, if you want to broadcast, for example, I want to create a. So this is a 3 by 2 array, and you want to calculate the sum of the 3 by 2 array and the 3 by 1 array. You find that the B 3 by 1 array has only one column, so automatically this one column will be duplicated and create a 3 by 2 array. Then you calculate the element-wise sum. Okay. So the array broadcasting can be illustrated like this. Okay. So so this is a 4 by 3 array. And the 4 by 3 array plus a 4 by 3 array will be 4 by 3 array plus 4 by 3 array. Okay, you have the element-wise sum to be calculated. But if you have a 4 by 3 plus a 1 by 3, then this 1 by 3 will be broadcasted to a 4 by 3 by duplicating all the values of the first row. Here, if you have a 4 by 1 array plus 1 by 4 array, you will have the 4 by 1 to be broadcasted and 1 by 3 to be broadcasted, both to 4 by 3. Okay, let's take an example and just practice it. Say A is np dot range a range. Let's say 0, 30, what? And by 10. And we reshape it. It's gonna be, it will be this, but I want to reshape it. So A plus A dot reshape 4 by 1. Then A is this. And what about B? B is 0 by, no, it's just do 3. Okay, and then B is this. So let's take a look at A plus B will give you exactly excuse me, exactly the same as what it shows. So the 4 by 1 matrix is broadcasted to 4 by 3, and the 1 by 3 is also broadcasted to 4 by 3. Okay, then we calculate the element-wise sum. Okay. So this is an illustration and explanation of the broadcasting rules, and now we talk about the vector operations. The inner product, outer product, and dot product. The inner product, well, if you learn linear algebra, you will find that this is like naturally true. Okay, for some of the people who have totally forgotten like what the professors have taught you in the linear algebra, I'll just repeat this. This is a U and this is a V. There were two lists, and you can use the function in Numpy inner product to calculate this inner product. So the inner product is calculated as this times this, plus this times this, plus this times this, and you got a 6. Okay. The outer product will be this times this as, so 1 times 1, which is 1, and 1 times 1, which is 1 times 1, and 2 times 1, 2 times 1, 2 times 1 here, 3 times 1, 3 times 1, 3 times 1 here. Okay. Okay. The dot product is a matrix multiplication. The inner product is a referring to a more general concept called inner product space. So dot product is a very special case in the inner product space in the real value. If it's a complex, so if your array has some complex numbers rather than real numbers, if you're major in mathematics and you learn the real analysis, you will understand the difference between the real number and the complex number. A complex number is like the square root of -1. Okay, it's a complex number. So so in this case, the dot product and the inner product, the two are the same, but the inner product will not be the same as dot product if the numbers are complex numbers. So here specifically, the dot product is this times this plus the element-wise multiplication as the sum of the results of multiplication. Well, inner product calculation can be different. It's the same as the dot product in this case, but it can be different in the complex values. Okay. Here is just to show you the transpose that we have talked about. Here is actually showing you the inner product, the dot product, and the outer product. You have A as and B is this. What is B? So A is this. A's transpose is this 2 by 3, and B is 2 by 3. And the NP dot is AB, so basically A times B is this times this. Okay, so how do I show you with? I hope that you can see this this yellow one. I think I'm recording it. So basically, it's this vector times this column. This row times this column. And that is 1 times 1 plus 1 times 1, which is 2. Okay, 2. So you also have, this is 3 by 2 times dot product 2 by 3 will give you a 3 by 3. And for each element, it's calculated as the 0, 0 product of how do I explain it without having a blackboard? This is really testing me. Okay. So this is calculated as this times this plus this times this. And this is calculated because the first row, second column is first row, second column. So it's this times this plus this times this plus this. And this is calculated as this times this plus this times this. I think it may be easier for you to understand I don't think the example is a good one. Let me I want 6 numbers. Let's do 2 by 3, and A is this. B is so A is this, B is this, and the inner product between A and B is 8. No, I should, A should be, wait, A is 2 by 3, B is 3 by 2, 2 by 3, 3 by 2. No, A is 3 by 2, I'm sorry. Is let's just use this tuple. This is what we learned in tuple. Okay, A now is 3 by 2, B now is 2 by 3. Okay, and inner product of A and B will give you this. So how do you calculate this 44? It's 8 times 1 plus, so it's 8. Okay, plus 9 times 4 is 36. 36 plus 8 is 44. Okay, how do we get the 61? It's 8 times 2, 16. Okay, plus 9 times 5, which is 45. That's 61. So in this dot product between A and B, if you want to know how you can get the number in the X column and X row and Y's column, X row and Y's column, you use the X column of A, for example, the second column of A, times the Y's column, this is the first column of B. So it's 1, 4. So it's 10 times 1 plus 11 times 4. Okay, you get 54. Okay, this is inner product. And you can show, well, I don't think that this example is really good, but it shows that if the BT is, so B is 2 by 3, so BT is 3 by 2. And A is 3 by 2. 3 by 2 cannot be multiplied by 3 by 2 because you must have A by B times B by C. So you will have A by C matrix. Okay. So this is universal functions, and as element-wise calculation, it's similar to what we talked above. How many slides do we still have? 1, 2, 3, 4, 5. Yeah, let's first talk about this. And you see, the binary operators, you can also use the functions to achieve the same goal, but the operators are obviously easier. So what is A here? What is B here? So A plus B will give you this. This is what we learned before. And what about... Oh, I probably need to have np.end. Okay, you got the same thing. And A minus B is also equivalent to np.subtract AB. Subtract, not subtract. Subtract AB. And you got same thing. It's equivalent to A minus B. This is remainder. A. Okay. Well, this is a warning because it's not really. Maybe I should use this. B is this. So B dot T is this. Let me C is B dot T. So C is this. A is this. Let me use A to calculate the remainder of A by C, and you will have so this divided by this, and it can be divided. 8 can be divided by 1, 10 can be divided by 2, and 12 can be divided by 3. But 9 divided by 4, you have a remainder of 1. Okay, you can also use a remainder to A and C to get the same thing. Okay, and this is a multiply, and this is divide, and this is power. Okay, power. You can try this by yourself, and let me just try it for you. Okay. Oh, sorry. I should do this. So, because A and B, they're not the same x by y. A is 3 by 2, and B is 2 by 3. So we should use a C also, a 3 by 2. So it's element wise. A is C is, so it's 8 to the power of 1, and this is 9 to the power of 4. Okay, the largest one is 13 to the power of 6. So it's 13 times 13 times 13 times 13 times 13 times 13. Okay. Yeah. The add and the other, I think we have pretty much talked about them, and let's end this in. Let's end this for now, and we will keep talking about the other things in the next video. Okay, the other things about Numpy in the next video. Okay, let's first stop here.